Hi everyone. Today we're going to be talking about clustering, which actually is the last section of this class, so I hope you are excited. Clustering actually follows quite naturally from classification, so a lot of the ideas that we've previously used are going to be transferred over to talk about clustering. So what exactly are we trying to do with clustering? Well, clustering really refers to a broad set of techniques that try to do the following. They are techniques that try to find subgroups or clusters within your data. So some sort of idea of subgroups. Within your data. Notice this is a bit different from classification, because in classification, we had the groups ahead of time. But somehow with clustering, we are trying to find these groups without knowing what they were ahead of time, which is, you can imagine this is a very hard problem, but one you might be interested in, right? We don't always know what the groups are. Right? So clustering in general, right, when we find these subgroups, right, we want them to have some nice properties, right? So in general, all of our clustering techniques, they aim at partitioning all of our observations into distinct groups. And this is quite important, right? It might seem kind of trivial that I'm mentioning this, but this distinct part is important. This basically means all the groups themselves are different. They're non-overlapping in some sense. Right, so we want to make sure our observations are all partitioned into distinct groups, so that what? So that all observations in the same group look similar. Right, that seems quite natural. And what would if we want all observations in the same groups look similar, what would we want about observations in different groups? Well, we'd want them to look very different. So, and all observations in different groups should look different. All right, this is not a specific algorithm that I've sort of talked about yet, but I think this makes a lot of sense, right? So we're going to say our clustering algorithm is doing well if the following happens. Well, one, it needs to make groups that look different, right? They're distinct, they're non-overlapping. Again, seems kind of trivial, but it's an important thing to mention. So all of our groups are distinct, right? And all observations in the same group look the same, right? So if I put you into a group, you should look like everybody else in that group. Then all observations in different groups should look different, right? So you look like everyone who you've been assigned to, but you don't look like anyone who is in a different group, right? I think this all sort of intuitively makes sense to us, right? Maybe we don't quite understand the algorithm yet, but we're going to get there. But just sort of motivates clustering a little bit. This sort of thinking is used quite a lot, right? And as you can imagine, a couple of things I've not sort of told you about yet that might be glaring questions for you is, what does this word different mean? And what does this word same mean? So I'll leave that as a question here that we're going to get back to. So a question, what does it mean to be similar? And what does it mean to be different? Those two are probably very closely related. But you can imagine that this notion of similarity and differences, right, is quite key for clustering, right? I've sort of based my entire criterion of how well my clustering algorithm is doing based on this idea of similarity and differences. So getting that right is going to be quite important. And we'll talk about some easy ways of at least approaching that. But let's motivate clustering a little bit, right? Is this even a useful thing that people talk about? Let's talk about a first example that I think is quite motivating. Let's say you have a normal data set, right? Data set I know normally looks like an Excel spreadsheet. So let's just pretend like I'm drawing one. Let's say I have n observations, right? So I have like n people, right? And then I have a bunch of data points I've collected on each one of those people. So everyone here, these are people. And for each person, I've collected information. Let's say right now I'm at a hospital. And all of these people are patients. You can imagine that I can collect information about their health, right? So let's just say that each of these people was getting screened for breast cancer. And I was collecting a lot of information about them, sort of related to breast cancer, right? So maybe our first observation here is the tumor stage, right? How far along is their tumor, right? That could be important. What's the grade of it? Right, and you can imagine I can collect a lot of other diagnostic information as well about them. So I'll just go dot, 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 dot. A lot of other variables. So this is one variable here, another variable here, right? And I have a lot of information about them. Now, it's maybe not too surprising to you, right? That, cancer is quite a complicated, it's quite a complicated disease, right? So cancer is complicated. And as you can imagine, cancer has a lot of varieties, right? So maybe it would be an interesting question to know if there are interesting subgroups of breast cancer within our data sets. Right? This is an actual question that hospitals are very interested in answering. Right? So a question here, I'll just write question. A question for the hospital could be quite simple. Are there any unknown subtypes of breast cancer in their data sets? Right? You can imagine if they can identify these subtypes, they can better treat people with those specific subtypes, right? Which inevitably is better for the patient overall, right? We can more directly attack the problem that they have instead of treating everyone in generalities, right? More like a personalized medicine sort of approach. And I argue that clustering can help us find these subgroups. And it's sort of nice here, right? Like we sort of became obsessed with knowing these groups ahead of time, right? We became obsessed with knowing these groups ahead of time. But sort of somehow now I'm going to find really useful information that I can use for diagnoses, right? Without knowing these groups, right? So I don't know what the subgroups of breast cancer are, but maybe my data set has information in it that can help illuminate this for me and help me make better decisions as a doctor. All right, so I think the health angle here is quite interesting. Obviously, this is also a business course, so maybe I'll give you one marketing example. So I'll make this example too. You can also easily imagine you work for a marketing agency, right? And a classic thing you have on marketing, right, is you might have a lot of observations. Let's say on customers. And some of this information could be like household income. Right, another one here could be occupation. Another one could be like distance from a city center. Right, and then your job, let's say working for a marketing agency, right, is you might wonder, it's the question the marketing agency might have, is that they might wonder what types of people would respond better to an advertising campaign. All right, and again, we don't know what those people look like ahead of time. We don't know what these types of people look like ahead of time, but I claim that clustering can help us identify groups of people that can respond better without us knowing what these groups are ahead of time. Right, so it's really quite powerful, and these applications sort of arise everywhere. If you remember back to our Google Maps example a couple weeks ago, Google Maps was very interested in clustering countries together, depending on data quality, right? So that's another reason why you might want to clustering. And these examples really will go on and on and on. So hopefully you can see that this is very powerful. This idea of being able to almost put people in the groups without knowing what the groups are ahead of time is a very powerful and useful tool in a lot of different applications. So there are a lot of clustering techniques, right? So there are many clustering techniques. And we're not going to learn about all of them. We're going to learn about, I think, the simplest and most famous one. Right, and everyone has their own riff on clustering. Similarly with classification, we didn't learn about all classification techniques, but we're going to learn about a very famous algorithm right now called the k-means clustering algorithm. Right, and what does this algorithm do? Well, this algorithm does exactly what I was motivating earlier. Right, it's a simple approach. That does what? It partitions our observations into k distinct non-overlapping clusters. All right, and that's the goal we had earlier, so it's great. It's great that it does this. K-means also has sort of one restriction. So what do we need to do with k-means before we start? That maybe is different than other algorithms, but it's quite important here. We need to decide on the number of groups ahead of time. So we need to decide on k. And here, this k is just, I'll write in a different color because this is important. This is just the number of clusters. And this is something you decide. Right, so that's quite important. You decide on the number of clusters to start out with. Right, you can decide you want one cluster. That's quite trivial. You just put everyone into the same group. You can decide you only want 2 clusters. You can decide you want 1,000 clusters. It's really up to you. Right, but the k-means algorithm relies on you picking the k, and you will always get exactly k clusters. Always, always. That's the algorithm. It's very good at giving you exactly k. So what your job is to assess what the best k is for your given application. This is not obvious. So I recommend you try many k's. You try many different values of k and see which one performs better in your current application, which one makes the most business sense, right? And we'll show you some diagnostic tools sort of at the end in Radiance, and that'll sort of help you better decide if the K you picked was good. But a lot of it really does take business sense. There's not always this like clear-cut rule as to what K is the best. All right, so we decide on K, and then restricted on that K, the k-means algorithm puts every observation, so puts every observation into one of the k clusters with a guarantee, with a really nice guarantee. And the guarantee is what? The guarantee is that the within cluster variation is small, or as small as possible, given your data set. I'm just going to write small. Now that's quite great, right? So, well, what is within cluster variation? This might seem kind of complicated. Well, this is, again, goes back to the motivation I had earlier. This within cluster variation, it's actually not that complicated. This really just means that observations in the same cluster are as close as possible. That's great. But how does k-means decide what close means? Right? I've still not told you what close means. There's a very, you can decide on a different way to define closeness yourself, and I can be convinced that there are many different good ways of defining closeness. And we discussed a lot of them in class, given certain applications. But a very typical one people use is something called Euclidean distance. It's a fancy name, but you'll need to know it because sometimes in software it'll ask you what distance you want. You're doing a quick Euclidean. This really is not that complicated. You can just think of it as the boring old distance you use in regular life, right? So if you had, let's say, I'll just draw some example, right? If you had point A here and point B here, right? The Euclidean distance between point A and point B is just the line that connects both of them, right? Quite simple. And you can imagine like this was easy to do because it's two-dimensional, right? X and Y, let's say. But then this might get more complicated when you are trying to get the distance in a higher dimension. Let's say when you have 3 or more variables, you can't really draw it. But the thinking stays exactly the same. It's just finding a line between all of those points. So it's quite simple. And I think it's very intuitive, but there's no need to sort of go too much into the math. But like I said, it's possible to pick other distances. It's possible, right? And I could be convinced that there are other good ones to do. As I said, Euclidean distance is the normal, boring old distance that you've probably used your entire life. So I wouldn't get too carried away. An example of something that would not be Euclidean distance, so let's be this red line. Like this is also a distance between A and B, but it's not Euclidean. This one's quite boring. And it's quite laborious. So we wouldn't measure something like that. Okay, and that's what k-means does when it talks about closeness. It just kind of gets the line between all the points. But what is the algorithm? So let's discuss the algorithm. It's very, very simple. You could have come up with it on your own. But know that the k-means algorithm actually will be done in the background for you, but it's very important to know sort of how it works. Just so you can diagnose anything that goes wrong, or maybe in the future you'd want to build upon it. Right, so it's good to know how the algorithm in the background works, but Radiant will take care of all of this for you. All right, so step 1. Your first step is to initialize. So by initialize, I mean you're going to randomly assign every observation to cluster 1 or 2, right, or k, right? And remember, this k is something you specified, right? So you came up with this. You specified it, right? It could be 10, it could be 2, it could be 1,000,000, right? You told me what cluster, what k you want. So we randomly assign every observation to one of these clusters, right? Again, that is a form of clustering, but it's probably quite bad. And the algorithm says, let's start with something that's quite random and bad, and let's make it better. Okay, so how do I make it better? The first step I'm going to do is compute what's called the centroid of each cluster. It's a really big word, but this just is literally the average of all observations in each cluster. And since right now we only have this random initialization, right, then the average is probably quite bad, right? So these centroids are probably quite non-informative, but hopefully we can improve upon this. So the first step, again, is to compute the average of these initially very bad clusters. And then after computing all these averages, I have one centroid for each cluster. And then I reassign all my observations to the cluster whose centroid is closest. Right? So now that I have all these centroids, I basically say, okay, let's put you in a new group, and I'll put you in the group where the centroid is the closest. Now, this might give me a slight improvement over random, but as you're thinking, it's probably not amazing. But you know what? What if I did this again? What if I do it again? Maybe I can keep repeating this process over and over again. And the hope here is that if I keep repeating this process, so I keep computing cluster centroids, reassigning observations, right, and then computing new centroids, and I keep doing it over and over and over again, maybe eventually these clusters will become really, really good. And that's exactly the idea of k-means clustering. So I'm actually going to repeat these steps, repeat step A and B. I'm going to iterate through steps A and B until cluster assignments stop changing. All right, so I'm going to loop. So I'm going to keep repeating steps A and B over and over again until my clusters are so good, there's no reason for them to switch. And that's what the k-means algorithm does. It's a very simple algorithm. And basically, it starts with randomness. And then we slowly keep improving upon that randomness through every single loop until my clusters stop changing. Right? So there's no more new assignments. And this makes the clusters as close as possible to each other. And this actually is, it's a simple algorithm, but it's quite powerful. And it's something that has only become useful or possible to implement due to the power of computation, right? So it's very, very cool and interesting to use. If you want to see this algorithm, sort of in a picture form, I will show you next, sort of as a transition. I'll show you this algorithm kind of in a nice picture so we can visualize it a bit better, and then I'll show you how to do this in Radiance as well. So stay tuned for a quick second.